All right, welcome back to the other side of the break. Again, we're trying to figure out how you're going to determine the richness in the community, given that you're going to have to look at a lot of quadrats. The more quadrats you look at, the more likely you are to pick up some of these rare species. If you don't look at enough quadrats, you won't pick up any of these rare species. And on the other side of things, if you put out too many quadrats, you've just wasted a lot of your time. So the question then is, how am I going to optimize this whole process so that I get just the number of species that are a good estimate of the number of species that are out there without oversampling? All right, so the technique I'm going to use is called rarefaction. Very nice technique where I'm going to use my own data to figure out if I did a good job or not. So we have the quadrats here numbered. Quadrat 1, quadrat 2, all the way down to quadrat X. And then in our spreadsheet, species 1, species 2, all the way through species X. Right? And I have this whole thing full of numbers. Okay? All right, so I'm going to make a plot. Along the x-axis is quadrats sampled, and along the y-axis is cumulative species number. Okay? Cumulative meaning I'm just going to keep track of the total number of species that I've seen across a certain number of quadrats. So, for example, if I don't look at any quadrats, I don't see any species. Then I'm going to randomly sample my data. And I'm going to ask the computer to pick a number at random between 1 and 245. 245 being the number of quadrats that were used in this particular field. So, let's say the computer says 16. I look at quadrat 16 and I count the number of species that I see. So, looking at one quadrat at random, let's say that I see 4 species. Okay? Then, I have the computer randomly sample what's left of the quadrats. Let's say it samples 186. I look at quadrat 186, and it says there are 6 species, but 3 of them I've already seen. They were in quadrat 16. So if I've already seen 3 of them, then this 6 species really represents 3 new species. So now, 2 quadrats, I've seen a total of 7 species. I saw 6 in quadrat 186, but only 3 of them were new. I'm only plotting the new ones, the cumulative number of species that I see. Now, what would I expect this plot to look like? I'm going to have the computer go all the way up to 245 quadrats, right? Randomly sampling them and plotting the cumulative number of species. So what would this curve look like? Well, I would expect early on that I would begin to pick up a lot of new species by just looking at one new quadrat. But early on, what I'm picking up are the common species, right? The ones that are easy to see because they're freaking everywhere in my field. I'm tripping over them. The common species are going to begin to be accounted for very early. The rare species are going to start to show up as I sample more and more quadrats. But the rare ones are only showing up every once in a while, so my guess is this curve is going to begin to asymptote. Big changes early on, and then it should start to kind of bend over as it asymptotes toward a particular value. The value that it asymptotes toward is the theoretical number of species in that field. Okay? Now, I can do this once, but I recognize that by sampling at random, I could get a particular shape curve by chance, right? I could get the one that increases the fastest or increases the slowest. So if I do this process a second time, I would get a second rarefaction curve, and that rarefaction curve might look like this. Because of the way I sample my data at random, I got something that looked like that. And if I did it again, I might get one that looks like this, and then again, and again, and again, and again, and again, and again, and again. So I do this a bunch of times by having the computer randomly sample my data. And each time I get a rarefaction curve. Well, now I should have somewhere in here the average rarefaction curve, and then around these values, right, I have some measure of the variability in all of this. The average rarefaction value is the one that the computer predicts is the magical number of species in the quadrat. If I just looked at 6 quadrats like I threatened to do in the previous slide, then my rarefaction curve 4, 5, 6 here would look like this. Well, that doesn't tell me anything because I don't know where this levels off. I can't estimate the cumulative number of species here because I don't have any idea of what this curve is doing. On the other hand, the more quadrats I sample, the more I give this curve a chance to level out. And if it's leveled out, then I have a pretty good idea that, hey, that's probably the number of species that occur. That's the richness because I've done a good job of sampling. If I did a bad job of sampling, I'm nowhere near close enough to this value that represents the asymptote. I really don't know the number of species in the community, and I can't estimate it very well. And if I oversampled, right, oversampling would look something like this. Right? I measured out 572 quadrats, but it pretty much gave me the same answer that 210 quadrats would have given me. I've spent too much time and energy on something and not gotten anything for it, not gotten any extra resolution. So, all right, so let's take a look at what we got for the Erie Bluffs State Park. We went out and looked at all of these quadrats. We did a rarefaction curve. Here's the rarefaction curve here. Coal is the cumulative number of species. And as you can see, the black line here represents the average rarefaction curve. And the green and the blue represent the error bars or the variation around that produced by randomly sampling the data. And here, measuring out 245 quadrats, we felt pretty good that the estimate of species is somewhere between 45 and 50 species. That's how many species of plants, vascular plants, we saw in the field that first year. We may not have seen exactly all of them, but the rarefaction curve predicts that that's the number of species that are there, and we were pretty darn close to that, so we felt pretty good that that's what species richness was. Okay? Rarefaction curves are nice to do because they give you some confidence in your estimate of the species richness of the community. All right, here's a rarefaction curve for a beetle in a young pine habitat. Again, the black line here, that's the estimated value as determined by the average, and the green represents kind of the variation of randomly sampling the data several different ways. The y-axis here should be cumulative species richness because we're adding more species as we add more quadrats. Okay? the nice part about rarefaction curves is you can use them to compare between communities. If you want to know which community is the most rich, that is, contains the most species, what you would do then is do rarefaction curves for each of your communities. A maple, pine, oak, second growth forest, tulip tree, maple, oak forest, cottonwood floodplain, jack pine, and birch forest. Again, notice how they're naming these communities based on the dominant species, except for this one, dominant species plus something about the physical factors, the fact that it's in a floodplain. Okay? And if you look here, their sampling in each of these communities shows us that the birch forest is very low in terms of species number, and I feel pretty good about that estimate because I'm already asymptoting on that line. And it looks to me like the maple, pine, oak, second growth forest has the most bird species in it compared to all of the others. Okay? All right. Don't think I have another one here. I don't. All right. So now we finished off with richness. Let's move into abundance and these abundance measures. So let's start with the first one, density. We said that was a measure of the number of individuals of a species divided by the area. And that gives us an idea of its density within the community. Right? The number of individuals divided by the area I looked at gives some idea of its density. Now, that measure itself is what's called the absolute density. That's number of individuals per area. Okay? We can also think about density in another way, given that we're talking about communities. So in communities, there are other species. So I may want to think about how my density for my species compares to other species within the community. Okay? So if I took everybody's absolute density, species 1, plus absolute density of species 2, plus absolute density of species X, and I took all of those together and I added up all of those absolute densities. Okay? That's going to give me the denominator. Didn't give myself enough room here. So this is relative density. And then I take the absolute density of species 1 divided by the sum total of all of the absolute densities for everybody, and that gives me a measure of the relative density as a percentage. Okay? So another way to think about this, let's say I have a forest here, and I went out and I counted 6, 9, 10. I counted 10 individuals of this species 1. Its absolute density would be 10 individuals per, and let's say this is an acre, that would be 10 individuals per acre. That's the absolute density. Right? Then what I would do is count up the number of individuals of everybody else. Let's say there are 5 individuals of species X, and there are 10 individuals of species dot. So I would take and sum up all of these absolute densities. 10 individuals of species 1 plus 5 individuals of species X plus 10 individuals of species dot. That's all the absolute densities summed together. And then for the numerator, I have 10 individuals of species 1. That's 10 divided by 25, which should be 40%. So the absolute density is 10 per acre. The relative density is 40%. That is, the number of individuals of species 1 represents 40% of the overall number of individuals, everybody included within the community. Okay? So we can think about density both as an absolute measure, how many individuals do I have, and also relative to everybody else. High relative densities would give me common species, low relative densities give me rare species. Okay? All right, that's density. Again, for some species, it doesn't make sense to talk about the number of individuals because individuals vary in size so much. There's a particular fungus that they tested for in the soil, and it covers the whole state of Oregon. It doesn't make sense to say one species within Oregon because it's such a huge species. We could talk about the side of a mountain being composed of all of these aspen trees. I could look at the number of stems as a measure of density, but it probably makes sense to think more about the overall amount of biomass. That would be a dominance measure. Okay? So we're going to do the same thing we did for density. Dominance can be measured as absolute dominance. And in absolute dominance, this is the area taken up by species 1 divided by the area that you're looking at. So for trees, this might make a lot of sense. I could take and look at the cross-sectional area of a bunch of species 1. Maybe these are all sugar maples within the forest. This is still an acre. The dominance would be the cross-sectional area of all of these individuals together. That's absolute dominance. It's a measure of area taken up. I could also do